Hello, we are Beyond Robotics, the first Greek team to participate in the European Rover Challenge. Our journey began in 2023 with TALOS 1, continued 2024 with TALOS 2, and this year we proudly present our latest evolution, TALOS 2.1. Both rovers are fully functional. TALOS 1 is now used in exhibitions and school visits to inspire the next generation, while TALOS 2 is under continuous testing and development to meet the demanding standards of the ERC. Beyond Robotics operates under the auspices of the National Technical University of Athens and the University of Patras, but our team brings together over 100 passionate students from more than 10 universities across Greece, primarily focused in the fields of computer science, mechatronics, and geosciences. Our structure includes 5 main divisions: engineering, responsible for building the rover through 7 specialized subsystems, each led by dedicated team leaders; R&D, which supports academic research, monitors theses and publications, and explores innovative solutions; operations, managing sponsorships and public relations; events, handling outreach and organizing our participation in the ERC in Poland; and human resources, which focus on recruitment and ensuring a smooth onboarding experience for new members. Participating in the ERC allows us to connect with a global community of innovators, continuously improve our technical and teamwork skills, and apply our knowledge to real-world challenges in space robotics.
My name is Alexandros Tasoulis Nonikas, and I am the lead system engineer. The systems engineering team is responsible for the integration of the subsystems. Our 5-member team is divided into 4 core sections: the management of requirements, risks, assembly, integration and testing, and the concept of operations. Finally, the systems engineering team is responsible for all the deliverables related to the European Rover Challenge. Although the TALOS 2.1 rover appears to have no significant differences at first glance, significant technological advancements have been made that considerably strengthened our system. In terms of mechanical components, the implementation of a 3D printed wheel on our mobility system has been completed. Regarding the processing power of our rover, the development of an autonomous navigation software to enable rover autonomy was completed. In a similar manner, software was developed for the autonomous movements of the robotic arm. Implementing these changes will allow our team to complete operations more quickly and efficiently, with the goal of achieving maximum points for each task.
The mechanical subsystem is responsible for the rover's chassis, the structural backbone, and its mobility system, which enables it to navigate varied terrain. This year, we strengthened the chassis by replacing the previous connections with ripped aluminum brackets, significantly increasing stiffness. We are also introducing a detachable electronics box that houses the computer and power subsystems. Combined with known payload position and weights, this allows us to fine-tune the rover's balance. In the mobility system, we upgraded the wheels to a 3D printed TPU-95A honeycomb design, developed and validated through simulation and testing. Finally, we are tightening the bearing tolerances at the boogie pivot points to eliminate leg tilt, especially during skid steering.
I'm Kostas Kagias, the leader of the electrical subsystem. This year, our focus was optimization and system resilience. The electrical architecture was refined to be more robust, efficient, and easier to maintain. The power system uses 2 lithium-ion battery packs with integrated BMS connected in parallel for redundancy and ballast load sharing. We have upgraded our power converters for better thermal performance and reduced losses, ensuring a reliable power delivery to every subsystem. A dedicated microcontroller handles real-time energy monitoring with voltage and current data stream to the central computer for diagnostics. Our dual safety system allows full power isolation or selective shutdown of moving parts both locally and remotely. Finally, we have improved electrical interfacing for payloads, mobility and robotic arm, ensuring precision control with reinforced connectors for harsh environments.
The TALOS 2.1 computer subsystem has also seen major upgrades with cutting-edge features designed to further enhance both performance and user experience. At its core is the NVIDIA AGX Xavier, a dedicated streaming computer that enables advanced object detection and motion planning. Building on the momentum of agentic AI, we have developed a custom AI agent that continues to grow, giving us direct control over core rover functionalities through a dedicated NVIDIA Orin Nano. Containerized architecture allows seamless service migration between onboard and ground station data processing. To achieve better maintainability and expandability, the firmware stack has been fully refactored. New peripherals and user interaction devices are also being integrated, ensuring a streamlined and optimized operator experience.
Our Telecom subsystem demonstrated its robustness in last year's competition. It operates over a 5 GHz ubiquity U6 mesh link, providing fast and reliable communication. Thanks to a dedicated antenna mast, we are able to maintain near line-of-sight connectivity in most terrain conditions. Looking ahead, we are actively exploring LoRa integration to expand control rate and enable low bandwidth SOR data transmission over even greater distances.
TALOS 2.1 features an upgraded SLAM system built on the trusted combination of two Intel RealSense D455 depth cameras and a T265 tracking camera. We are continuously improving our mapping performance and Aruco tag detection. Our GPS fallback system has also been refined, ensuring more reliable navigation in challenging environments. With real-time terrain analysis, TALOS estimates traversability on the fly, helping it avoid obstacles and choose the best path forward. For strategic planning, we use the a priori map provided by the competition, guiding TALOS on a high level throughout its mission.
Hi, I'm Vangelis and I'm responsible for the drone subsystem. We're a team of 6 split into 2 groups, one that builds the drone and the other that works on the autonomous mission. This year we did Stello and build our own drone, Meet Infinity. It has a custom 3D printed frame, 6S battery and motors, a SpeedyB stack and GPS, all dimensioned with our own calculator. Its brain is a Raspberry Pi with a wide-angle camera module, and it communicates with the ground station via Mavlink and Wi-Fi. The drone runs R2 Pilot, is capable of stable flight and autonomous missions, and we have performed a variety of simulations and tests. Position keeping, Aruco detection and ground station GUI are ready for use, and we're now developing software in MATLAB for probe detection and high-level decision making. Once virtual tests are completed, we'll move on to real-world deployment. Our next goal is to build our own flight controller and battery pack.
My name is Ioannis Gavrelatos and I am the leader of the Payload subsystem. Our team consists of 50 members who are responsible for design and construction of the drill, the sample storage and the robotic arm with all its different end effectors. So far, we have redesigned the motor mounts in the drill, which has improved the smooth operation of the lifting mechanism and make the system easier to maintain. We also did cable management to avoid the risk of them getting cut or damaged while the mechanism is moving. In the robotic arm, we improved the design of the joints to make it more robust and stable. The end effectors were designed to complete the new ERC tasks and include a tool for measuring pH level, a tool for interacting with a maintenance panel, a tool for probe tasks, and a multi-purpose tool that can perform 3 tasks: collecting surface samples, rock, and the deep sample. In the next steps, we will run many tests for all major tasks, including maintenance operations and sample collection to fix anything that needs improvements.
A multi-criteria approach was utilized throughout the landing site selection process to combine effectively different engineering as well as scientific parameters. Additionally, an extensive astrobiological data analysis will be performed, and by utilizing a weight matrix, the most suitable pH sampling location will be identified. The rover's robotic arm, along with dedicated end effectors on board cameras and drill, will collect soil, rock samples and data from the Mars yard. The carousel will be used for sample storage and further analysis.
The science subsystem's main objective is to analyze geological data from Mars yard, focusing on unraveling the terrain history and testing hypotheses about West Candor Chasma. The selected landing site satisfies all engineering constraints and offers significant scientific interest due to its complex stratigraphy, evidence of fast faulting, collapse, and sedimentary processes.
Ωραία. Ωραία.
It was at this moment that he knew he f***ed up.
Oh.